Hello everyone, I'm Mike Joy from the Institute of Governance and Policy Studies at Victoria University in Wellington, New Zealand, and I'll just go to share screen and get started on my talk. Okay, roughly what I'm going to talk about is, I guess, that the biggest extraction that we all know about is extracting fossil fuels. And I want to talk about how we use those fossil fuels to feed a huge proportion of the people in the world, and how in that process we are destroying the life-supporting capacity of the planet. We talk a lot about the initial harm of the extraction, but I want to talk about a secondary harm. I mean, we know the secondary harm of fossil fuels on the climate, on the atmosphere, but I'm going to talk about the example of synthetic nitrogen, an area that I've been working with in relation to the harm that I've witnessed and written about over a few decades now of the secondary effects on ecosystems. And I think we need to separate out extraction of renewable material, so growing food as plants, for example, as very different to the extraction of non-renewable resources, both for the obvious unsustainability of extracting non-renewables, but also their secondary impacts. And I'll kind of finish up with this really big looming issue that we want to stop extracting fossil fuels, but the renewable energy utopia that people talk about is going to require even more extraction to get to that point, and we have to really face the reality that we cannot keep growing. So what's often referred to as the green revolution, I think it's kind of an arrogant view that we somehow were extremely clever and managed to feed so many more people. What it's really about is the ability to be able to take energy stored over millennia and turn it into food now through the ability to be able to create urea or nitrogen fertilizer, taking nitrogen out of the atmosphere to produce fertilizer. And you can see, just going back over the last 120 years, the growth in the correlation between the growth in world population, carbon dioxide emissions, nitrous oxide emissions, and the use of fertilizer, and then just the growth in anthropogenic, or the synthetically made nitrogen that now exceeds what natural systems, natural nitrogen cycles produce. We humans now exceed that production. And to give you an example of just how, it's known as the Haber-Bosch, named after the two guys, the two Germans that invented this process of being able to take natural gas and use it to make nitrogen fertilizer. Happened around the early 1900s, that started to ramp up really, really quickly. But I think the big take home from this graph is that that kind of browny, reddy dotted line, which is the proportion of the world's population that is fed through nitrogen fixed synthetically, and it's about half of the global human population is fed by this extractive process. There's another way of looking at it there, that the red part in the top of this growth in population over the last century, and how much of the world's population is fed by synthetic nitrogen fertilizer. So it's a really, really big part of the growth of the human population. And of course, there's some big inequities in this. We have a billion people starving or inadequate and insecure diets, and on the other end, 2.1 billion people obese or overweight, from that ability to be able to produce all that food, and the ability using fossil fuels to refine it, to make oils, and the increase in meat in our diets as well as a total. So we have a food system that's dependent on fossil energy, not just the fertilizer, but also the production system, the planting, the working up the land, the transport, refining, packaging, refrigeration. so we have incredible inequities there and inefficiencies. And the USA is probably one of the extreme examples. There were a couple of studies now that have shown to produce 1 calorie of food in the USA, or 1 unit of food energy, uses 21 units, or in this case, calories of fossil energy. So incredibly inefficient use of energy to power the human population. And it's making us more and more dependent on fossil fuels. And the other part of that is that I'll touch on again later, is that this concept of energy return on investment, not economic or financial investment, but the energy return on energy investment. From the time when we first kind of discovered oil in New Zealand off Taranaki, where it bubbled up out of the ground, and it was around 70. That means it took about, for every 1 barrel of oil, say, that you used, then you would get 70 back. And that has been reducing over time as we've taken all the easy stuff, and it's down to about 15 globally now. So 1 barrel to get 15 back. And that's an average. And in many cases, for example, tar sands and fracking, it can be way, way less than that, where you're virtually getting nothing back for the amount of energy that's being put in. And we, once, as I've said, once we started eating that oil, then we started that massive population increase as well. And just to give you an indication of the impact on the planet, on the biodiversity of the planet, I guess, on the biology of the planet, is the ratio of humans to the animals that we eat in our the biomass, measured as the biomass or weight of animals on the planet. And I mean, it's probably a good idea at this point, if you hadn't heard of this before, to think about what you imagine would be the balance between wild animals and the animals that humans eat, and our pets, but the domesticated animals. And it's a shocking 98% is humans and the animals that we have to eat. In this graphic here, we've got a breakdown: domestic livestock, cattle, humans, and then wild animals down the bottom there. 2%. So you can imagine that the impacts that this has on biodiversity, even without climate change, we're not even beginning to see the impacts of climate change in comparison to this imbalance here, where there's just it's so imbalanced towards humans. And if you want to see, an indication of the impact of that, of all those, of that conversion of, if you go back a couple of hundred years, it was utterly the reverse of that, where humans and what we ate were a few percent, and 98% were the wild animals. And here, this graphic here shows the planetary boundaries work that I'm sure you're all familiar with, but the idea of the green part of the circle here being the kind of safe boundary, also the kind of image that Kate Raworth uses for her donut economics with inside that green circle. But you can see some of those cycles, that those planetary boundaries that have been exceeded there, and the worst ones are nitrogen, phosphorus, genetic diversity, freshwater use, land use change. But the crucial part of this graphic here is the black dots, and the black dots from this paper indicating the impact or the role that animal agriculture has in the breaches of those boundaries. So we can see there that animal agriculture is a huge part of the breaching of the boundaries, and especially those the nutrients, nitrogen and phosphorus. And it's not that we couldn't feed the world without synthetic nitrogen fertilizer. We could, but the trouble is we use animals, and we have animals dominating our food systems, and they are so inefficient in their conversion. So for example, here, this is just to give some numbers, start off with 100 kilogram of fertilizer applied to the soil. More than 1, maybe up to 3 kilograms ends up in the atmosphere as nitrous oxide, which is 300 times more potent than carbon dioxide as a greenhouse gas. And nitrous oxide is also ozone depleting. And for every 100 kilograms of that fertilizer, there's a huge amount of embodied energy in that as well. So, and there's carbon dioxide produced from that process. But you can see how wasteful it is there. So you take in the pasture, that the cow's eating. So that's the fertilizer going on to grow the grass. And 75% of that energy that went in there is wasted as urea from urine. And this is where we start to get the impacts that I talk about, that I want to show you in our freshwaters in New Zealand. So they're leaky systems that we have, these farming systems that are intensive because of that applied fertilizer. So just going back to that graphic, roughly about 17% of the nitrogen applied ends up in the food. The rest leaks out into the environment to do harm. And you can measure it in the same way as you can measure carbon dioxide in the atmosphere. We have reduced nitrogen in the atmosphere as well. So from 270 parts per billion pre-industrial, now up to 320 and climbing. We see the eutrophication, the impacts on waterways in our rivers and lakes. So that, here's an example here with this filamentous algae, but we get algal blooms, and in the ocean we have eutrophication dead zones covering huge areas of the world. And the little graphic at the bottom there showing that increase in those dead zones, where basically it's about nitrogen, algal growth sucking up oxygen out of these systems and killing the life supporting capacity through having oxygen fluctuations or low oxygen that kills everything. Just to jump to New Zealand now to look what these systems look like here. So you can see the darker reds in this, the blues are the natural levels of nitrogen. These are rivers in New Zealand, and you can see the darker red are the areas where we have really intensive agriculture, mostly intensive dairy farming in New Zealand. So we ramp up the numbers of cows per hectare or animals per hectare by providing this fertilizer to grow grass faster, and we also import huge amounts. We're the biggest biggest importer of palm kernel in the world as a country, and I don't even have time to get in another extraction there that has huge impacts, biodiversity and human impacts. But that's what it looks like for New Zealand. So it's really easy to see what's going on and the impacts on our rivers. And it has further effects as well. So you can see here, this is looking at the actual measurement of nitrogen in rivers and then modeled out, and you can see again those intensively farmed areas and most of those red areas exceeding the level for nuisance growth, and it affects our ecosystem health as well in our freshwaters. Again, the map looks almost the same. These are everything that's orange or red is either moderately or severely polluted, using the macroinvertebrate community index, our way of measuring ecosystem health in rivers in New Zealand. Another way of looking at it from the Ministry for the Environment's guidelines webpage, these are the orangey rivers or parts of the country do not meet the guideline for nitrogen in rivers. So that's what we see on the surface waters. We also have many, a high proportion or nearly all of the lakes that are in agricultural catchments have very high levels of nutrients and are eutrophic or have undergone harm from that eutrophication from those nutrients. Just to narrow down again to a really recent case study here for Canterbury with unlimited intensification that happened, and basically turning a dry area into farming using another extractive process, and that's taking water from aquifers and rivers. And this graphic here is going to hopefully, if it works, go through time, and you'll be able to see the changes. So look in the bottom right of the map there, you'll see 1969, and once I start it should start ticking over. And look on the map, you'll see the orangey areas. You can see around Rangiora and just north of Christchurch City, some little orange patches on the map there, and a few down. Then in the 1990s, you see this sudden increase. What these are is conversions from dryland farming into dairy that has been enabled by irrigation. Massive centre pivot irrigators. Anyone who's been down there in the last few decades will have seen these things or flown over it. Conversions to dairy farming and taking water. So Canterbury is now, the irrigation, the amount of water irrigated in Canterbury is higher than the rest of the country put together. And there's just a massive change that's happened in that time. And as part of that process of having to put those irrigators in, then all of the trees had to be chopped down to allow this to happen. And the trees were all parts of shelter belts that the region's notorious for its dry northwest winds that blow across there. And removing those shelter belts now mean that the evapotranspiration rates increase, so that by the time you get over about 20 knots of wind, then the evapotranspiration rate exceeds the rate that the irrigators can put the water on. So another kind of example of the idiocy of what's being done here. But it's done for capital gains. It's done because of a lack of government regulation. But it's just incredible growth that's happened since the 90s there, since the arrival of the Resource Management Act, actually. Okay, so there are some huge human and ecosystem health impacts of that, and we're only just starting to realize the human health issues because the science takes a while to catch up with reality. So a few studies have come out recently in Europe. This one I've got at the top here, nitrate in drinking water and colorectal cancer, is a big one from Denmark, where millions of people were involved in this study. They had good data from levels of nitrate in drinking water and population-based data on colorectal cancer. And what they found was that at about, at 0.87 milligrams of nitrate per litre in drinking water, you have a significant increase in the risk of getting colorectal cancer. What we have in New Zealand, actually in most of the world, is the maximum allowable value is 11.3 milligrams. So the maximum allowable value for nitrate in drinking water is based on some completely different harm, which is the blue baby syndrome, just for young children when they're changing from their mother's oxygen supply and blood to their own, they're susceptible to this. So the maximum allowable value is actually 10 times or more than 10 times higher than the level where you get an increase in the risk of getting colorectal cancer. And you can look at that paper there in the article in the conversation if you want to look at more details on that. Michael Baker from Otago School of Medicine and I wrote that article. So I'm going to show this same graphic showing the increase in nitrate, increase in farm conversions, but I'm going to show you the increase in nitrate in groundwater from 1971, when the regional council started collecting that data from bores. And so I'll start the graphic going again. The years are down the bottom right, and you'll see as we go through time, the bars pop up when they exceed 2.1 milligrams, which from the Danish study and others is the area where you have is the level of nitrate in drinking water where you have a 15% increase in the risk of getting colorectal cancer. So you can see how quickly that nitrate moved through from the conversion to dairy into those groundwater samples, and almost everyone in this region drinks. The drinking water supplies, both private and public, groundwater. So that is going straight through to the drinking water, and I'll give some examples of that as well. But another way of kind of measuring that is to think about the grey water footprint, or how much. It's just a way of trying to get your head around the problem is to work out how much nitrogen is lost to water from those systems, and we have a measure of that. And then how much water would you need to dilute that? The ecosystem health limit for rivers is in flux at the moment, but will be around the 1 milligram. So to meet 0.8, which is to say under that risk of colorectal cancer in drinking water, for every kilogram of milk solids produced in Canterbury, you need 90,000 litres of water to dilute the ecosystem impacts of that. The current literature talks about 1,000 litres of dilution per kilogram as a guideline kind of level the numbers coming mostly from industry. But when you work out this grey water end of it, then it's more like 90,000. So to give you an idea of how much that region would need to change, you would either need 25 times more rainfall, and even if you include the non-dairy areas, then you still need 17 times more rainfall than has at the moment. The plains receive 17 times more nitrogen than what could be diluted to safe limits. So obviously, well past any safe levels there. And this is just some information from Ministry for the Environment. You can see that Canterbury region down here. I don't know if this cursor shows up on the screen for you, but this is the South Canterbury region. You can see here that nearly all the bores exceed 3 milligrams, which is more than 15% increase in the risk of getting colorectal cancer. And all these orange or red ones means that the trends are for them getting worse. So not many sample sites from the North Island, so we can't really talk about what's happening there, but extremely bad in Canterbury. And just to give you a picture of the actual drinking water, so the graph on the left is 393 samples from 2005 from drinking water in Christchurch City. And you can see I've got the two lines in there, the significant risk and then the 15% increase in the risk of getting colorectal cancer. You can see about half of Christchurch City dwellers receive water over that significant risk. And once you get into the Canterbury and the rural areas there, then most of the people in the rural areas are receiving drinking water from their public water supplies well in excess of the increased risk of colorectal cancer. And if you want to look at the cost of that, then if you start working out health costs, the European Union have worked out that the cost to human health and ecosystems and biodiversity is estimated 70 to 320 billion versus the added value of the fertilizer of somewhere between 20 and 80 billion. So you can see there's just nil sum gain from nitrogen fertilizer if you start to put in the externalities into the equation. And similarly in New Zealand, and we published a paper on this showing that if the dairy industry had to pay the costs of not the health costs, just the ecosystem health costs or the costs to ameliorate those impacts on fresh water and the environment, then there would be a nil-sum gain. It's actually a loss to the country allowing this to happen, because the costs are not passed on to the industry, then they're just left for future generations to deal with. And just to kind of make the point that this is not, that we do have other options here. Up until the 1980s, we didn't have nitrogen, synthetic nitrogen fertilizer in New Zealand. We used clover to fix nitrogen. And you can see there that from an energy point of view, from a greenhouse gases point of view, and from a pollution point of view, then just grass and clover without nitrogen fertilizer has much better outcomes for the environment. And there's another key nutrient for growing plants and at the intensive level that we do, and that's phosphate. And definitely that's reaching the limits of extraction as well. And pretty much the bulk of what is left is in the Western Sahara. And we in New Zealand import that, but it's been in the news quite a bit lately. It's been called blood phosphate because there is some significant human rights issues around who owns that phosphate, and because at the moment, or for the last for the time that New Zealand's been buying it, has been coming from the Moroccans, and the Moroccans the UN has made a declaration that the Moroccans are illegally obtaining this phosphate. So effectively, we are receiving stolen goods. So I want to just quickly touch on the limits to growth, the limits to extractivism, really seeing this is what the conference is about. And I just wanted to give this example here of, and this is from a recent textbook in Springer, published by Springer, that I can share with people if they want. But here's a bunch of metals that are required for electric vehicles. And what we have on the little boxes on the left for those metals are the annual production at the moment. It's all been relativized to the reserve base, so the boxes in the middle that are all the same as what the known reserves for it. And the boxes on the right show what is needed for batteries to convert the fleet of cars that are currently on the planet to electric vehicles. And you know, there's if you look at the annual production and what's required, then you can see the big anomalies there. But the other big anomaly is we just don't have enough of it. There is no, for example, nowhere near enough cobalt on the planet to be able to make those batteries. So these are just, apart from all of the other reasons why we can't convert the whole world to electric vehicles, this is just one of the limitations. The other limitation on being able to do any of this stuff is the energy return on energy invested that I touched on in the beginning. And this graphic here shows well that the combined impacts of that declining return on energy plus the resource pyramid, which means the conundrum here of the rarer something becomes, the more material you have to process to be able to get that. So on the left, we have the example of oil. So the easy stuff at the top, and this is you know, in the crude oil. So the higher energy return on investment at the top of that pyramid, and then as you go down, the energy return on investment for Canadian tar sands down at 1, where it costs you 1 barrel of oil for every barrel you get, so it's just not worth doing. So as we move down that, because we have to you know, fight harder and harder and harder to find it. We've got all the easy oil, now we're getting into the hard stuff. And then the other pyramid on the right that just concentrates all those problems. And the example here is from copper. And as copper, or as any of the metals become harder, you have to process, you have to extract more and more and more to get the same amount of product at the end. And the combination of those two things means that the amount of material that can be extracted is diminishing fast. So just to kind of sum up, that I talked about what these are manifestations of limits to growth. So the limits to extractivism. We have the animal agriculture footprint, the fact that all the easy fossil fuels have gone, but we've also got this reality of climate change that we need to be carbon neutral by 2050. So we're going to have to stop extracting those fossil fuels anyway. And the reality of that is that without fossil fuels, we won't be able to extract most of the other non-renewables that we do at the moment, because we won't have the energy to be able to do that. And just to kind of, to finish off my talk, I wanted to kind of just give a quick reality check. To me, this is the simplest way to understand that reality of declining fossil fuel energy. Is if we take the year 2018 and convert the fossil fuel energy use, which is 97% of the energy on the planet that we use, then in 2018, roughly just rounded off to 11,000 megatons of oil equivalent fossil fuels. And if we want to do this, get to carbon neutral or zero carbon by 2050, that gives us about 11,000 days. So we've got to reduce 11,000 megatons in 11,000 days, so 1 megaton per day to do that. And if we want to think about, well, what's a megaton of oil, then we would need to build 1,500 big wind turbines, or not just build, but place 15 and wire up and connect to the grid, 1,500 wind turbines every day for the next 11,000 days. And just to give you an idea of the scale of that, that's about the spacings that they're needed would be about 700 square kilometers of wind farm every day, but just to give an idea of also, if you want to go to nuclear to do it, one large nuclear power plant every day from now until 2050 in 11,000 days. Just a hint of the reality of how hard it was going to be if anybody thinks that we're just going to go from fossil fuels to renewables over that time. Okay, so that's the end of my talk. thanks very much. There's a couple of books there that have details on the stuff that I talked about around nitrogen. There's a chapter in the New Zealand Land and Food Annual called Our Deadly Nitrogen Addiction. And I also have a lot of information on that waterqualitynz.info website as well. So I'll just stop that sharing. Thanks everybody, and I hope that the conference is going well.